Problem 6-102. Consider the graph at right. Is the graph a function? Explain. So we're looking at this graph right here as it goes up and down, and then back up. They want to know, is it a function? First of all, we need to ask ourselves, what exactly is a function? So I've kind of laid out a little bit here. Remember, if we were talking about functions, the first thing we want to speak about is a relation. A relation is just a set of ordered pairs. So a bunch of points on a graph. A function, though, is a relation, so a bunch of ordered pairs on the graph, in which every input has exactly one output. In other words, there are no 2 points with the same x-coordinate on the graph. So as we look at our graph here, remember our x-coordinates going left to right. Are there any 2 points on this part of the graph where they have the exact same x-coordinate? Now, one way you can check this is what you probably used to use in Algebra 1, is they used to call it the vertical line test. You go through here and you take your pencil and just kind of trace over your graph and you look to see, does it intersect more than at one point in the entire way through. And you see here, it only touches it one time at most as you travel along back and forth along the graph. So therefore, we could say that this graph is a function because there are no 2 points that have the same x-coordinate. There's no point directly above or below another point. Letter B says, make a sketch of the inverse of this graph. Is the inverse a function? Justify your answer. Alright, it's a little tougher sometimes to draw the sketch here when they actually haven't given you coordinates, because you either have to make up your own coordinate system and then flip-flop your x and y values to draw in your inverse function, or you got to come up with another means. The way I do it's a little different than probably what a lot of people have done here, but what I have here is I have just a little segment here that is perpendicular to our line y equals x. Remember, the line y equals x is going to be that line of symmetry between our original function and its inverse. So it should make somewhat of a mirror image of this shape here across this line. But I like to take this, and if you think about it, when you stare directly in a mirror, right? When you stare directly in a mirror, you get your reflection straight back at you. So I'm going to use this perpendicular line, it's perpendicular to my line of symmetry, to help me come up with my points. So before I do that here, I'm going to mark out what my important points are on my original function. We'll do that in red. So this is an endpoint. It's always good to mark any kind of endpoint that you're dealing with. Looks like it's about to hit, the line of symmetry. Anytime it crosses either of the axes, we want to make sure that we take that point into account. So there's a point here, any point where it changes directions. Anytime it touches that line of symmetry. So you see I'm just kind of marking some points here. Oops, that one got a little off there. Let me move that one. Oh, I guess I get to do them all again. And we got one here, and then maybe one up at the end there. So you see, these are the points that I would consider to be the most important, because these are the ones that are easiest to mark as you're trying to draw them. So here's what we'll do. Let's take this perpendicular line, and I'm going to take it here, and I'm going to see, well, I intersected my first point. I'm just going to trace it right along the line of symmetry. So that means I'm going to have a point that's probably about the same distance to the line of symmetry, so we're going to put it about right here. Now I don't really have to worry about coordinates, I'm just looking at the distance. Is it an equidistant from my line of symmetry? Now let's move on. You do want to keep track of the order in which you put them, so if you want to number them, you could do that. So I know here I'm going to hit, boom, I hit this point here, which means I'm going to have a point about the same distance away. So I'm going to put this point right here. And let's continue on. Looks like we got a lot of points coming up here. So our third point looks like it hits, this is our third point right here, which means we're going to have a point that's pretty much equidistant from there. So it looks like it'd be about here would be fine. And then we look like we have about 3 points in a row here. Let's see. Let's take it and let's move it on here. Yeah, so we've got this point, and this point. So remember the next point here is this one, so that means we'd have a reflection across, which would be this point also. And this is the point where it intersects, and then it's going to hit over here as well. So we kind of got all those ones covered. Now let's just continue on down. Let's go until we get to our next point. Looks like, bam, we got one right there. So let's draw that one in so it's equidistant to the line of symmetry. It looks like we're going to have another one here. Let's see if I just move it on a touch. It's probably too far. Oh well, we're going to go with it. And let's see, this one is farther out, so probably about somewhere out here would be okay. Remember, this is a sketch, so it doesn't have to be exact. We're trying to be as close as we can. We've got a point on the line of symmetry, so let's put that point there. And as we go through the line of symmetry, we know that we want to end up on the opposite side of this one, so we should have a point over here. I'm just going to move my perpendicular line out of the way. And now I'm going to do my best just to kind of sketch it and follow the points there. When you're done, it should look very similar to the other one. Just remember, it's just the reflection. This is difficult. This one always drives me crazy when I try to do this, but I apologize ahead of time if it looks awful. Don't judge, though, because I'm not going to judge yours. So we got this. That point. I have to come this way because I can't draw it the other way. Oh, come on now. I'm better than that. Apparently I'm not. One more time. Oh yeah. Woo! All right. And we're bouncing off this axis just like they bounced off the axis here. So we're going to bounce off this one. And we're going to go in towards our line of symmetry, out, and then back across. So that's just a way to kind of help you out with trying to draw the line of symmetry there. I know mine's a little crooked and this and that, but I'm happy with it for now. So they ask us to sketch the inverse of the graph. Now they say, is the inverse a function? Well, remember, the same principle applies here. If I took this and I looked at put a vertical line out here and I look to see, right now it's only intersecting at once, but when I get over here, you see I have 3 points here that will have the exact same x value in terms of their coordinates here. And then I go on, now I'm down here and I have 2. So this is definitely not going to be a function because you see there's many points there that have more than one output. So like this x value would have more than one output. So is it a function? I'm going to go ahead here. I cheated a little bit this time just because I was having trouble fitting everything on here. So the inverse is not a function because there are some input values with multiple output values, as we just looked at. Or you could say that there is more than one point with the same x coordinate and different y coordinate. If that makes sense there. So letter C. Must the inverse of a function be a function? I love this question. Obviously, the inverse of a function does not have to be a function because we just proved that on our graph, right? The first one was a function, but this one was not a function. So does the inverse of a function, does it have to be a function? No, it doesn't. Stupid question. Just kidding, there's no such thing. Right? Letter D. Describe what is characteristic about functions that do have inverse functions? All right, so I'm going to give you the answer here first, and then we'll talk about it a little bit. It says functions with inverses that are functions may not contain any points with the same y coordinates. If you think about it, I'm going to kind of draw one off on the side over here. If we think about, if we had a coordinate plane here, we know a parabola is a function, right? And if we were to take 2 points, and let's say this was symmetrical, I know it's not drawn the best here, but let's say we had a point here at -2, 2. Then we also had a point over here at 2, 2. Well, think about on a table here. We'd have an x, we'd have a y. We'd say, all right, we have a point at -2, 2. And remember, a parabola is a function. And we also had a point at 2, 2. So two different x's can have the same y's, but when we look at the inverse, what happens is when we flip our points, these two y values that were the same become x's. So when those become x values, now we have a problem. This is not going to be a function because we have two inputs with different outputs. So you can't have the same x coordinate in two different points. It's not a function. So that means that any function that kind of goes up and down and actually ends up having 2 points with the same output values, the inverse of this will definitely not be a function because of it. So when we say functions with inverses that are functions, so anything that actually has an inverse that is a function may not contain any points with the same y values like this one did. All right, hopefully that helps there with that. If you wanted to think of one that was, think about like a line, you know. If you did a line, it doesn't go up and down, you know, there's no points that have the same y coordinates there. Ask your teacher if you need more help with that. All right, let's go to letter E. Could the inverse of a non-function be a function? Explain or give an example. Well, that's easy. Think about this. Here we have a function, or I'm sorry, an inverse or just a graph that is not a function, right? This is not a function. But we know that the black one is the inverse of our blue one, you know. So if we had started with our blue one here, we'd say, well, that's not a function, but its inverse is a function. So functions here. So once again, let's state the obvious. If we can get this little rectangle off of there. The graph we sketched above is not a function, but its inverse, the one we originally started with, is a function. So yes, it is possible. Here's your example. You've already done it. All right. This one, I have a feeling, is dragging on there. I tried to make it as short as I could by including all this extra information there. Hopefully this helped you out. This is problem 6-102. Thanks for watching.